Okay, good morning, everyone. I'm going to get started here. We begin lecture module 3 today, storage. Of course, lecture module 2 was due this past Sunday night. I have not graded yet this morning, so I don't know if any late submissions came in. I'll do that immediately after class, so please check your grades. Again, on the Linux labs, they're pass fail, 1, 0, 1 meaning pass, 0 means fail. And really don't take it as a fail, maybe take it as something needs correction and resubmission. And again, it's very important. We need to establish that everyone has the necessary understanding concepts to move forward. So I understand, of course, mistakes will be made throughout the lab as you work through the lab. Don't worry about these. I'm really just expecting that the exercises themselves be correct when you get to those those screenshot submissions. Of course, the screenshots will have other information where you may have made a mistake. That's fine. Again, it's critically important that everyone remains on pace. One of the largest contributing factors to people not succeeding in this discipline is if they fall behind. So please remain on pace. As I've stated before, you remain on pace, you're going to have the full time for the final project. You'll have full credit for Linux Lab final project. Your final grade will reflect that. It'll be very good. I do see something in the chat. Again, I have the chat minimized, so if you have a question, please speak up. I'll get to the chat questions, of course, following class, but otherwise I can't sacrifice that screen space, so I'll move forward. So I'm going to begin with the textbook information, of course, chapter 3 from the Understanding Computers textbook. And I'm going to jump right in. So, not in the textbook, as previously presented, is Kreider's law. We know about Moore's law. That was in the textbook. Every 18 months, computer processing power doubles and takes up half the space. Kreider's law, which is equivalent to it in terms of storage, Kreider's law has kept pace with Moore's law. And this has many ramifications and repercussions when we get to, say, big data, just the available storage on our personal devices. So, and we'll take a look at this as well. I brought this slide forward from this chapter into the previous chapter. So we've seen this before, the memory hierarchy. We know that the fastest circuitry in the computer, of course, is the CPU, operating billions of cycles per second, gigahertz. We know it's very expensive. Okay, so I'm talking about the register circuitry that complements the CPU, actually exists on the central processing unit. We know there's a big discrepancy as we move away from the CPU, say out to storage, our hard drives. So we have many intermediate levels to hopefully keep the CPU fed with data and instructions. And recall what I said, the major limiting factor today is the interconnections. And I'm going to illustrate this very shortly. Now, again, it's called the memory storage hierarchy because we move from memory, it's from the CPU to the cache to RAM. And at some point, we get to storage. And we understand the distinction between memory and storage. And again, I try to provide all of the terms that may be used. We know volatile and non-volatile, right? Memory is volatile. You turn the power off, it goes away. We know that storage, the hard drive, is non-volatile. Okay. I can also use the words, and you'll see these words in textbooks, as persistent and non-persistent. So volatile memory is non-persistent. Stable storage is persistent. We know that storage is static. A program sitting on your hard drive is static. Okay, it's just sitting there. Whereas a process in memory is dynamic. It's being executed. We know that all execution takes place in memory. So again, if I have a piece of data out on a hard drive, I want to change a word, in a Word document. That document or a portion of it needs to be read into memory. You can change it then, and then needs to be written back to storage. So we have to understand and recognize that there are actually two communications. To change something on the hard drive, I need to read it in and then also write it back out to storage, okay? And this is going to have major implications on the efficiency of our computer. When we evaluate storage, it's very similar to what we look at in, say, the memory hierarchy, right? There's always going to be a trade-off. I presented that it would be great to have a computer built entirely of register logic, that quick, operating at the same clock cycle as the CPU. Nobody could afford it, okay? There's always going to be trade-offs in the design of any computer system. We're going to see actually that it even applies to operating system design. So the textbook presents characteristics to consider: speed, okay, compatibility, and this is huge, storage capacity, convenience, portability, can we take it with us? Absent from the text is cost. And we're going to look at this down the road because we will do cost benefit analysis to determine what may be best for us. We need this type of efficiency, but we have limitations on what we can spend. Also, whenever we talk about the storage system, or similar in the last chapter, the system architecture, we must almost necessarily at least speak about or reference the operating system because of the close coordination between the hardware and the operating system in the functioning of a computer. We'll look at that with compatibility. I can look at USB drives. USB drives can be used in Mac, Linux, or Windows. It depends how they're formatted on whether they can be read by those systems. What does the formatting? It's the operating system. So again, it's very difficult to speak just of storage without bringing in a discussion or an introduction on the operating system constructs that manage the storage system. On that note, we have the logical versus physical representation. Okay? The logical file representation is how individuals view the document. This really is or requires that we talk about the operating system. It is the operating system that presents this logical file representation. Okay. It also presents an abstract view of the file. The physical file representation, as we see, is that the operating system will manage this, as files will be strewn, for lack of a better word, across the storage system. They will not be represented or stored in their entirety contiguously, which means one after another. Quite often, largely, they will be separated across the physical storage system, and they'll be stored where there's free space. The operating system manages this free space and the file system. Going back to the logical file representation, again, this is how we as users perceive files. I think of an .mp3 with a .mp3 extension. It's a song, right, or a music file. .avi, .mp4, it's a video file. .docx, docx, it's a Microsoft Word file. .pdf, it's an Adobe PDF. So we're going to see that this logical abstract file representation is managed by the operating system. And this is actually the most conspicuous part of the operating system, and I'll present this when we get to operating systems. Largely, end users are not aware of, or nor do they care about where a process may be in memory while it's being executed, or how many CPU cycles it's getting, how the time slicing, the scheduler is actually working. Typically, end users are dealing with files. Okay. Again, the physical file representation is how it is stored physically on the device in the medium. Volatility, random, sequential access. Well, I've already introduced volatility, right? We have volatile memory, non-volatile storage. Random versus sequential access. This used to be easier to teach back in the day when people were still using cassette tapes for music. Okay. Inside a computer, memory, random access memory, right? It's byte addressable. I can go to any byte or word, however, within memory directly. Random access is also known as direct access. In some textbooks, you'll see it as direct access. Our hard drives, our USB drives, are direct access, but not at the byte or word level. We're going to see that they are addressed on the cluster or the block size, which is much larger. Okay. Sequential access. Sequential access is our tapes. So we still use them in our backup tapes. And the best example, again, was that cassette tape, that music tape. And if you've ever had a cassette tape, I know they're incredibly dated these days, but to find the beginning of a song, what would we do? Fast forward, is that it? Nope. Fast forward, is that it? Nope. Fast forward, up, I went too far. Rewind, rewind, up, too far. Fast forward, okay? You can see the sequential access and what this would require to access, say, the beginning of a file, beginning of a song. So to some extent, we are jaded in that we just expect random access now with our file system. I want to play this song, this movie right now, okay? Don't want to waste any time. We're going to look at sequential access because it actually will have other impacts, say when we get to, say, database management systems. So the file system and the file is an operating system, OS, construct. Okay, can be anything stored on a medium. Okay, and we're going to see there actually is a distinction between the storage medium and the storage device. And I'll introduce that in just a minute. The file name is typically given or created by the user. And we know this, right? If you create a Microsoft Word document, you name the file. But it's not necessarily the end user. If you've ever downloaded something, your operating system may ascribe a name to it, or it may have a name associated, which may not be meaningful from the download. We know about extensions, .mp3, .docx, .xlsx for Microsoft Excel, okay? And typically, they're associated with an application, but not necessarily so. This is operating system managed, and not all operating systems will attribute or actually associate an extension with an application. Okay? This is overhead. We'll actually have to assess this when we look at operating systems. Folders, okay? Previously known as directories. When I began studying computer science, they were directories. Along comes Microsoft, and they essentially renamed directories folders. So many contemporary users think of them as folders. We know in our Linux labs, we refer to them as directories. Of course, Linux, and the basis it comes from, Unix, predates Windows. A note on Linux. In Linux, there are actually only two types of files. Okay? They're regular files and executable files. And we're going to look at this. This is coming up in a lab or two, and we'll take a look at this. Okay, so when we look at storage system characteristics, we have the medium and the device. In some cases, the two are inseparable. In others, we naturally think of them as separate entities. Looking at storage mediums, we have magnetic, electronic, and optical. And these correspond to, or an example of a magnetic medium is the hard drive. An example of the electronic medium, flash, SSD, the USB thumb drive. And then optical, of course, would be the CD or DVD. The device is where the storage medium is located. And again, sometimes in some units, we don't think about separating them. The USB thumb drive. Nobody would think about taking a USB thumb drive and opening it up to get to the solid state device, okay? Actually the electronic storage system. Similarly, a hard drive in a computer. Of course, you can take the hard drive out in its entirety, but nobody can or should open up a hard drive to look at those magnetic platters. You're almost certain to crash that hard drive. In contrast, a DVD or CD, we naturally think of them as separate. I have a CD or DVD player, and then I have my collection of DVDs, right? So there is a separation between the medium and the storage device. Storage systems characteristics. Okay, when we look at, again, here, these slides here, what we're really looking at is the operating system construct, the superposition of the operating system on to the storage system. Because now I'm looking at the file system. We're going to see in the operating system, there are many managers. There's a scheduler that manages the CPU, a memory manager. There's a file manager. And again, the file manager is probably the most conspicuous part of the operating system. It's what users interact with. I want to play a song, right? I double click on some song.mp3. I want to play a movie, same thing. I want to open up my Microsoft Word document, okay? So users naturally interface with the file manager of the operating system. It's the operating system that determines the file system. And we're going to see this if you ever format a drive. It's the operating system that is formatting a drive to a particular format. So here we have, the folder perspective of, say, Windows. Here would be, say, the Explorer, Windows Explorer perspective that allows us to navigate, find files, things of this nature. And then this you should recognize from the Linux labs. This is the Linux file system. The Linux file system, as portrayed here, is an upside-down tree. And we typically look at file systems depicted as a tree, upside-down tree. So of course, if it's upside down, at the very top of it is the root, R-O-O-T. The root of the Linux file system is denoted with the /. And I see the subdirectories. Bin, short for binaries. Many of the executables of the system are here. Okay, the various programs that you're actually running in your Linux labs. Device, where I mount devices. Okay, this is in contrast to Windows. Okay, Linux file systems mount devices, much as the Mac operating system, which is based on Unix, mount devices. And we'll look at this in forthcoming Linux labs. We have home, okay, where essentially user accounts. We're going to look at this. I'll open up my terminal here in just a minute. Also, etc., library, and user. So on that note, I'm actually going to open up a terminal here. Actually, I'll get out of here. Control C. Oh, actually log out. Okay, so clear. There we go. So, oh, you're not seeing that yet. Give me a second. I can find my terminal on my Zoom screen here. There we go. Okay, so this is my terminal on my MacBook Pro. And you actually see this. Again, we're learning in our Linux labs to look at the prompt because it's going to tell us where we are. You should know the tilde is our home directory, right? And get back to my home directory, cd tilde, okay? And I typically don't say space when I say this and speak about my Linux commands here. So let me connect to the acadnx server, username at the domain acadnx.hvcc.edu. Okay, prompt me for my password. Of course, I do not see the password as I type for extra security, and that should look familiar to you. We're going to see some of these things later, by the way. You have mail, okay? But now you can see from my prompt where I'm located. And I could do an ls. Okay, there we are. That's what your system is actually going to look like at the end of the semester. But let's do some navigation. cd space ... Go up a directory level. Linux informs me where I'm at. Well, I'm jlubiat at acadnx, and I'm now in /home, root home, okay, in that subdirectory. I can do an ls, and I see every CISS 100 student. I'll go up again, cd space dot dot ls. And now take a look at this, bin for binaries, dev, home, etc., as well as some other things. Okay, user. So we see that. And I'll jump back now to my Google Chrome here. So I just showed you, of course, I was down here at this level. I cd space dot dot moved up a level. Okay, so now visible was with an ls was everything in that home directory. I gave a cd space dot dot and moved up to the root directory, and then I could see everything within that. And we introduced the term the namespace, okay? Because in computing, we talk about deterministic computing. No ambiguity is allowed. I need to completely specify everything, or be able to completely specify everything. Because again, in the root, I do have an etc. subdirectory. But if I look down here, in local, I have an etc. subdirectory. But these are different namespaces. The namespace of this root directory is all the files and directories within it at that one level. That's it. So at this level, I could not make another directory called etc. If I was at the root level, I could not go make dir, space, etc. It would not let me because it already exists. However, if I was to traverse or navigate down to user, say into any one of these other subdirectories, I could make dir. I couldn't do it in this one. There's already an etc. there, but I could do it in others because they're different namespaces. And we talk about fully qualified path names. So look at this etc. This is //root, etc. This one here is /user / etc. We separate directories with that /. This one here is uniquely qualified, introduce that term, as /usr /local etc. Okay, so you can see how those three etc. subdirectories are all distinct in their fully qualified names, their path names. Okay, so again, with the mediums, three mediums: magnetic, electronic, and optical, that correspond to the hard drive, solid state device, and digital video disk. And we saw with quantum computing, by the way, that the qubit can actually store things. Okay, so there's something else coming on the horizon. And we know that Harvard is also using DNA as a storage device. So again, with all of these things, how do we assess them? Well, what's their speed, their compatibility? Again, compatibility is going to largely depend on how they're formatted, which again is an operating system function, their capacity, portability, and of course I added cost. So let's look at the three mediums and really their associated devices as well. And we'll begin with the hard drive, the magnetic hard drive. Okay, it still has the most, it's used by most systems. We've seen, of course, phones, tablets move to solid state storage, and there are advantages, many advantages. Of course, the disadvantage is the cost. Solid state devices are more expensive than hard drives at this juncture. Okay, we categorize when we learn a discipline. So hard drives can be internal or external, can be encrypted. I'll actually add they should be encrypted. So you never know. You never know when your computer will be stolen. I don't know everyone's computing practices, so I don't know if you're say saving and autofilling passwords, but think about that with a computer. Yes, there's a login, okay, username, password, but if I have a computer in my hands, okay, I can crack that password, just brute force. It may take me some time. I'll just run a program. I will crack it. So God forbid you don't, encrypt your hard drive. And you say have password autofill checked in your browser. So what is and how are magnetic hard drives put together? One or more permanently sealed magnetic disks. Well, we'll just focus on the more, okay? We have read-write heads, and the best way to describe this actually is to take a look at a device. So we know in the magnetic hard drive, okay, we can magnetize the surface to represent zeros and ones, right? The von Neumann architecture, the basic representation within the computer. So here's a picture. Now again, it's not going to be a single platter. It's going to be many platters stacked up one on top of each other. Additionally, the platters will be read to and written, or read from and written to on both sides of the platter. Each platter will have two read-write heads, one on top, one on the bottom. The read-write head is on an arm, okay, or let's say access mechanism, which will allow the read-write head to be moved in towards the interior of the disk and out towards the exterior as the disk spins underneath it. Again, the best way to describe this is taking a look at the picture. So here we have a hard drive depicted as 4 disks or 4 platters. Again, there will be a read-write head on top of or on the top surface and a read-write head on the bottom surface of each of the 4 platters. So in this case, we'll be reading and writing 8 bits at a time. The platters have concentric circles, okay, which means, of course, they meet each track. The tracks are further divided up into these pie-shaped pieces called sectors. Now, really, a sector is the smallest addressable space on a hard drive, and it will be comprised of 512 bytes. But with the size of today's hard drives, we can't even have, it's difficult to maintain the address space if you're addressing at each individual sector. You know, terabyte drives, divide that by 512 bytes, and the number of addresses you have is enormous. And recall, all processing is done in memory. So if you want to find something on a hard drive, well, you need its address. That address, those addresses need to be in memory. So they're consuming memory that you'd otherwise use for processing. So it makes sense to combine sectors into clusters. And with this, the cluster will become the smallest addressable unit. Typically, the minimal cluster size you're going to see is, say, 4 sectors, right? The sector is 512 bytes, so 1024, 2048. 2048 bytes will be the smallest addressable cluster or unit on a hard drive. Now think about this. We understand what needs to occur. I can't process anything that's sitting out on a hard drive, right? It has to be read into memory, which means now my minimum size, I need to read 2048 bytes in, even if I want to just change one little word, 32 bits, okay, or 64 bits. Change it and write it back out. And we're going to see the discrepancy in time here is really going to impact how efficient our computer is. Recall my statement. The interconnections, and this is just a statement, it's not in any textbook, interconnections are often thought to be the limiting factor in computing. And I'm going to demonstrate this in just a minute. So again, here's my hard drive, the magnetic disks, read-write head, top surface, bottom surface of each platter. I have a read-write arm that moves in and out. And of course, these platters are spinning underneath that read-write head. A thing to note, the spinning of the platters, 10,000 RPM, okay? That's a mechanical device. Consider that in contrast to our CPUs operating at, say, 3 gigahertz, 3 billion cycles per second is a long ways away from 10,000 rotations per minute. They're chasms apart. The read-write head is a mechanical device that moves in and out. So we're talking about mechanical latencies. So if we look at disk access time, what is disk access time? Well, what actually has to happen? Okay, my read-write head may be out here on one of the outside tracks. I want a piece of information that's on one of the inside tracks. So that read-write arm has to move. And then it has to wait for the disk to spin underneath it. So what do we have? The seek time is known as the read-write head movement, okay, to the desired track, typically around 3 to 12 milliseconds. Milliseconds, 1,000 times a second, in contrast to the CPU's 1 billion times a second. Rotational latency. We have to wait for the desired track or sector to rotate under, okay, or cluster, excuse me. So again, with a device rotating at 10,000 rotations per minute, it's going to be about 3 milliseconds. And then we do transfer it, and the transfer rate is a lot quicker, because now we're talking about megabits per second. Okay, again, the lowercase b, we know it's bits, but of course we know file sizes are in bytes, capital B, so we know how to evaluate that. So to understand the discrepancy of that memory hierarchy, well, again, for us as humans, we can't even comprehend 3 billion cycles per second. We actually have difficulty with tenths of a second. We understand it in races or hundredths of a second, you know, the Olympics, things like that. But can we really see it? No, we need a photo finish to really even realize that. So what if we compare it and make one clock cycle of a computer to be equivalent to 1 second? Because we can understand seconds, okay? Putting it in kind of our human frame of reference. So what are we going to have? Well, if we look at the access time of a hard drive, it's in milliseconds, okay? My CPU, 3 gigahertz, billions of cycles per second. I know there's 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. And I can just do the math. So 3 billion divided by 1,000, divided by 60, divided by 60, divided by 24, essentially 34 days. Let that sink in. If the CPU was operating as a clock tick as 1 second, it would be waiting 34 days for a piece of data to come from the hard drive. That's the memory hierarchy, okay? That's why we need all those intermediary levels, right? There's a big difference between RAM and the CPU speed. So we have the L1 cache. There's a big difference between the RAM and external storage. So we're actually going to see that we're going to create a disk cache, okay? So the disk cache consists of memory, RAM, okay? And it's used kind of as a temporary storage area. And it works largely because we have something in computing known as locality of reference. If you're taking programming and logic, you know that the default execution is sequential. Executes one statement, goes to the next one, executes the other, etc., on and on. We have selection structures, if then else, switches, things like that. But even then, that locality of reference is going to be rather small. Or if we call a function, a subprogram, execution will jump to that function, but then within that function, there's also a locality of reference. Typically, files, yes, they are distributed across a storage system, right? So a particular file will not be located all contiguously on tracks that are all adjacent to each other, or sectors that are all adjacent. A portion will be here, a portion will be there, all over the place. But large portions will be adjacent. So it makes sense. If I need a piece of data from this particular track, I'm just trying to show it with my mouse there, quite likely the next instructions or the next pieces of data I need are adjacent. They're coming in the next sectors or clusters. So it makes sense, since my read-write arm is already there, I don't have to move it. I'm not going to incur additional latency, mechanical latency. So I'm just going to let that disk roll rotate under my read-write heads. I'm going to keep reading and writing and then transfer to the disk cache at that 1000 megabits per second and just fill that cache up. So should the CPU need that next piece of data and it's in the disk cache, grab it from that disk cache. Don't go back out to that mechanical hard drive. So again, we can improve performance in that way. Okay. As I said, it's very difficult to speak about storage or even architecture without some mention of the operating system, because the operating system is what controls and provides that level of abstraction for users to use the system. So, filing system will determine the partition size, cluster size, maximum drive size, etc. Cluster size, again, is largely dependent upon what addressing, okay? How large are the clusters? Of course, with more sectors in a cluster, my address space goes down and all processing is done in memory. So I'm using less memory to provide index addressing to my storage device. That's a good thing. I have more RAM for processing. The trade-off, of course, is as my clusters get really large and I need to change one little thing in a file, a database file. I want to change one piece of data. Well, if my cluster is 16 sectors, okay, 32 sectors, I need to read all of that into memory, okay? So there's going to be a larger slowdown than me reading, a 4-sector cluster into memory. So when we look at these, the file system, what it imposes, okay, the formatting. In Windows, we talk about the file allocation table, file allocation 32, and recall, we're also interested in portability and interoperability. Mac uses the HFS, hierarchical file system, which is, it's very nice, it's very good. But if you format a USB drive using HSF, you're not reading it on a Windows computer. I meant to highlight Windows there. In contrast, it's not as effective or efficient as the FAT32 exFAT, but it can be read by all operating systems, portability. Linux, this is not in the textbook, and I just included it just so you know. Let's take a look at partitions here, partitioning. We partition a hard drive, okay, or a USB drive when we format it. What partitioning does is it will take a single physical hard drive and turn it into 2 logical hard drives. This has several benefits. One, when especially if I partition a hard drive equivalently, I create 2 hard drives that are the same size, my addressing is going to be more effective, right? Because my cluster size is going to shrink. So that's one thing. We need to assess or keep in mind that IT business society triangle. A lot of the things we do because of the business ramifications or the societal ramifications. Companies that produce computers, Dell, Gateway, all these, Hewlett-Packard, started partitioning the hard drives that they sold to the end users, the consumers. And on say, a very small partition, they would create an image, okay, an exact replica of what was first installed on the computer. Why do they do this? Because they recognize there are business advantages to it. One of the things, and we're going to look at this down the road, is help desk IT support. Help desk is pure overhead, right? You've sold a computer, and now you need to support it. You need to hire technicians for your help desk staff. Those help desk staff are not selling any additional computers. You have no revenue coming in for that help desk functionality, but you're obligated to provide it. Quite often, it's very difficult for help desk technicians to understand what lay people are presenting to them. You've seen this in the Linux labs. At the bottom of the Linux labs, we have statements on what's required for assistance. I will get emails, Professor, I'm having problems with Linux Lab 3. It provides me with no information whatsoever. I can only guess at what's going on, right? So we require, hopefully we're teaching help desk constructs. Well, what step are you on? Please provide a screenshot, any supporting screenshots that may have gotten to that point, because then, much like a computer, I can deterministically assist. I know what's going on. I can see what's going on. Now you think about the general public. The general public has very little awareness of their system. Just even the help desk technician trying to give instructions and walk lay people, the common public, through something is very difficult. They don't know how to navigate their file system. They don't know how to do these things, and they will make mistakes. So getting back to partitioning, what these companies realize is they can create a small, essentially partition, and include an image of what first shipped with the computer. So should someone call in with a help desk request, and maybe their system has been compromised or something's gone wrong, they can merely say, please allow me to reset your system to its factory settings. And the user, because that may be the only recourse, the user will say yes, and that help desk technician is now off the phone and assisting someone else, rather than spending 1 hour with a single customer who may never understand the instructions they are being given. So there is a pure business advantage to following this course and partitioning a hard drive and providing an image with a replica of what was first shipped with that computer. So there's that recovery partition. Mac for a while was offering you the option of dual boot systems, because of course Mac can support Windows. It's not really on Windows because Windows cannot support Mac. It does not go the other way, which I'll speak about, by the way, when we get to software engineering or software design, cybersecurity, forensics, because on a Mac, through virtualization, you can actually run Windows, you can run Linux. On one machine, one box, you can run all of the operating systems. The same cannot be said for the other two operating systems. So Mac did have a dual boot option for a long time. It still is there, but there are better options now through virtualization. And I'll present and introduce virtualization when we get to operating systems. Hard drive file systems, again, this is an operating system construct. It's already presented, the FAT, the Mac, HFS, etc. Interface standards, now we're getting back into the hardware. Serial ATA, serial attached SCSI, okay? And note this, again, serial, 1 bit at a time, in contrast to what occurs inside a computer, which really we have parallel buses. And you think, why wouldn't we have parallel out to the hard drive? Because it's so slow, we want to speed it up. Well, we want interoperability, okay? Serial, just like networking, is that lowest common denominator. It's easy to support, rather than a 16-bit or 32-bit hard drive. Oh, sorry, it's not compatible with your system. I'm going to stop here, because I realize I do let people out late many times. And we'll complete this, and then I'm actually going to do some advanced things tomorrow as well. So that's it for today. Thanks, and see you tomorrow.